We usually associate biological electricity with rapid speed and sudden shocks. When we think of electrical power in nature, we typically look for fast, nerve-like reactions. The electric eel operates as the baseline for this assumption. It uses stacked electrocytes to generate up to 800 volts of biological voltage in a fraction of a second. On a smaller scale, the Venus flytrap uses action potentials, plant nerve signals, to convert an electrical spike into movement, snapping its jaw shut in milliseconds. Equating electrical power purely with speed overlooks a different biophysical achievement. In certain systems, the measure of success is long-term charge persistence. The cactus is the opposite of these fast-acting bioelectric triggers. It is a slow, stationary organism operating in a restrictive environment. Biological models often describe the cactus's thick skin as a physical container meant to hold internal water like a balloon. Standard survival models often categorize traits like sharp spines as a single-purpose defense mechanism against herbivores. The cactus functions as a massive biological capacitor. Its entire structure is optimized to hold a stable, long-term electrical state against its environment. We can see this mechanism by moving beneath the skin and looking into the microscopic interior cells of the plant. The water inside these cells acts as a dielectric medium. A dielectric medium is a material that stores an electric field through the displacement of its internal charges, without allowing current to flow freely. This intracellular water acts as bulk storage. The thick cuticle insulates it, preventing charge leakage. At night, an inverted photosynthesis cycle drives slow ion cycling. This separates internal charges into distinct layers, maintaining deep electrical gradients. This insulated structure ensures that electrical shifts do not spike and dissipate. Instead, they persist for days with minimal leakage. Moving outward from the core, the physical geometry of the cactus dictates how this stored charge is managed. The exterior ribs of the plant are dynamic. They mechanically expand and contract based on internal water pressure. This expansion changes the distance between internal charge layers. By shifting its geometry, the cactus actively alters its own capacitance to stay stable as the environment changes. Zooming into the spines reveals a specialized electrical interface layer. The sharp points of the spines function as distributed lightning rods. They concentrate the electric field at their tips to prevent an uncontrolled buildup of charge on the plant's surface. This architecture relies on fractal nesting. Fractal nesting describes a geometric structure that repeats its own pattern at smaller and smaller scales. This repeating geometry redistributes the density of the electrical field while regulating the exchange of temperature and airflow at the surface. The physical shape of the plant is an impedance matching system, tuned to stabilize internal charge against external desert conditions. Biological traits often emerge as stable configurations of energy and material. In the desert, the most stable configuration is one that resists change. A saguaro cactus can maintain this stable electrical state for over 2 centuries. Its ability to hold internal gradients correlates with its survival in a high-stress environment. We see similar patterns of slow throughput and stable structure in other long-lived species. The bristlecone pine uses dense, highly ordered wood to maintain structural integrity for 5,000 years. Millennia-old olive trees rely on a massive distributed trunk architecture to preserve their vascular systems through extreme droughts. Organisms optimized for high-speed signaling, like the Venus flytrap, require high metabolic turnover. This rapid energy use leads to a faster accumulation of cellular noise and a much shorter lifespan. The persistence of these plants is tied to their ability to hold a stable internal charge. By using geometry and insulation to minimize electrical leakage, these systems maintain coherence across centuries.